This is part 3 of a series of videos I'm making for Year 10 Science on motion. This is graphs of motion part 2. So let's look at the following graph of displacement S, let's say meters, and time on the x-axis in seconds. And I have a graph like this. A typical graph, a trapezium. Suppose I have the following times. Now bear with my diagrams and my scales, they're not accurate, obviously. Okay, suppose time is going up by 2 seconds and the displacement is going up by 2 meters. And I want to go from this to a velocity time graph. Now, the time always stays the same, as I mentioned in the previous video. Time doesn't change, so it goes up by 2s once again. That's your starting point there. I want to go from displacement S to velocity V with an arrow on top because it's a vector. Vectors are things that have a number, a size, and a direction. So this is meters per second. So this graph here of displacement and time tells you that overall the displacement is 0. Because suppose the origin here, the starting point, that's my home. I go drive all the way to work, to school, and then I stay at school for a certain amount of time. Okay, ignoring the seconds, pretend this is like, I don't know, minutes or something. And then for some reason I have to go back home. And then I go all the way back down to the x-axis. Okay, so I go to work, stay at work, and I go back home. Okay, that's what that 0 down here means, the origin. Origin means starting point. So we need to know what the relationship is between displacement S and velocity V. The formula sheet would say velocity V is displacement S divided by time. So we need to find the rise over run. We need to find the gradient of this graph. Now the way you do it is, you break up the graph into 3 sections. I see a triangle here, that's one shape. A rectangle here, that's the second shape. Another triangle, third shape. You need to find the gradient, the rise of a run, the slope of each of these 3 areas, okay, to make things easy for you. So the first area here, velocity will be for, so I'm going to do this, velocity sub 1. Okay, the velocity for the first area will be rise, which is 6. Okay, 6 over run, which is 4. And that's going to give me 1.5 meters per second. The second area, the velocity for this, the second shape, the V sub 2, it's going to be rise of run. The rise, once again, is 6. And the run, be careful here, between 4 and 10, there's 6 seconds, okay? So that's 6, and then you get 1 meter per second. The velocity of the third shape, triangle here, rise of run, the rise is once again 6. The run here is 2, because 12 minus 10 is 2. So you get 3 meters per second. And that's it. All we have to do now is graph it. Now the velocity is going from 1 to 1.5 to 3. So let's go by ones. 1, 2, 3. I'll extend this a bit and I'll make it up to 4. One, 2, 3, 4. So for the first area, the velocity is 1.5 meters per second from 0 to 4 seconds. From 0 to 4 seconds, it's 1.5. So if you look here, 1.5 is between 1 and 2. From 1.5 to 4, stop there. So that's a flat line there. So a velocity time graph usually looks like a box diagram sometimes. Typically like a box diagram, as you'll see, or it can be a straight line as well. But you'll see it typically as a box diagram, as I'll show you. Then the second shape, the velocity is 1 meter per second between 4 and 10 seconds. Now we have to be careful here. There's sudden jumps between velocities. So 1.5 meters per second up to 4 seconds, and then it jumps down to 1 meter per second. Okay, so you go down like this. Use a different color just to distinguish. Down to 1 from 4 to 10. Okay, keep your eyes on this as well up here. See what's happening. The third shape, it's 3 meters per second. So if between 10 and 12, it's 3 meters per second. You go back up to 3 and a flat line there. Okay, because it's constant velocity. Okay, 1.5 meters per second from 0 to 4 seconds means it's a flat line, 1.5. And similarly for the 3 meters per second and the 1 meter per second. And that's your velocity time graph. Then suppose you need the acceleration time graph. A for acceleration, the units are meters per second squared. Time once again stays 0, 2, 4, 6, 8, 10, 12. And what you'll notice here, the acceleration, because the velocity is constant throughout the motion, it's a flat line. And acceleration by definition is the change in velocity over time. Change in time, which is just the rise of a run. The slope, the gradient of a flat line is 0. So your acceleration will be 0 from 0 to 12 seconds for the whole time. You can put numbers here if you want. It'll be 0. There's no acceleration. So to summarize for a trapezium graph for displacement versus time, you always break it up into sections. So there's 3 sections in this case, 3 shapes. To find the velocity, use the formula. V equals displacement, velocity equals displacement over time. You plot the relevant velocities here. Okay, and you put, so this is like a box diagram. You put straight lines for constant velocity and sudden jolts, which are like vertical lines to indicate there's a change in velocity. And if there's constant velocity throughout the motion, then therefore the acceleration will be 0.